Okay. Okay, let us begin. Oh, someone remind me to give the quizzes back. I keep forgetting. I keep logging them around. At the end of class, I want to give quiz 3 back. And in terms of the last quiz, by the way, you should remember that I'm dropping 2 quiz grades. Of course, the diagnostic doesn't count here. So with quiz 4, which is the quiz you took last time, which is not graded yet, after that point, your best quiz grade is going to be your quiz grade. So you might see a little bit of a bump in the grades, hopefully, after that point. But then it's up to you to keep that up. So let's continue. We've been dealing with limits for 2-3-ish weeks at this point, and now we're kind of going to go away from them, but not completely. Limits are important. They're always going to be important. In fact, limits link the 2 branches of calculus pretty much just as much as the fundamental theorem of calculus does, but we're kind of not going to make them the absolute focus at the moment. We are going to fry a big fish today. We are going to solve the rate problem. So remember I told you calculus had 2 branches. One is called differential calculus. The point of that entire branch of mathematics was to solve a problem called the rate problem. The second branch is integral calculus, meant to solve the area problem. And that's something we'll talk about closer towards the end of the semester. But for now, we're going to spend a while dealing with solving the rate problem in various instances. Now, many ways to state this. Often it would depend on context, but essentially the goal is to figure out how fast something is moving. Or to say it in slightly a little bit more abstract term, figure out how fast a quantity is changing, especially in relation to some other quantity. You might have heard calculus is the mathematics of change. I don't particularly like that description, but it is true in this case that things change over time, and sometimes we want to measure how fast these changes are happening. That way we can plan for the future, we can really understand some sort of fundamental process or phenomenon based on how fast it's going, and if we make changes to something else and the speed of a process responds to that, that can tell us about the link between these 2 processes. So figuring out how fast something is moving is a very important thing to be able to figure out. Now, it's a very vague question, so you might ask, how could you come up with a way, a general way of figuring out actually how fast something is moving? Let's illustrate the idea that we're going to use. So we're going to start with an illustration. It's going to be an example, and we're going to make it very suggestive. And I've probably given a similar example to this already, but sometimes solve it blur. Suppose we have an object, or we're tracking an object. Moving at a constant rate of speed. So the whole time we're tracking this object, it's not speeding up, it's not slowing down, it's just moving at the same rate. We may not know what that rate is ahead of time. At a constant rate of speed. And we find the following. So let's say we're tracking the distance of that object over time. Let's make time here. Let's say we're tracking the distance on the vertical axis. Let's give this some units here. Let's say we're measuring time in hours. Say we're measuring distance in miles. So we're tracking this object. It starts at some location we deem position 0. at time 0, and then it sets off. And we're tracking this object, we're tracking its distance over time. So we might be tracking it, you know, after 1 hour, after 2 hours, after 3 hours. We track it after 3 hours, and we notice that it is 150 miles away from the starting point. Because it has a constant rate of speed, the distance is changing at regular intervals just like the time is, and so we end up with a straight line describing the distance traveled of this object over time. So now, here's a question. So we care about this problem, we realize that a straight line actually abstractly describes this problem, and so we start to study this problem by, of course, studying the straight line. So when you study a straight line, things that are of interest start to become obvious. You might ask the question, what is the slope of this line? What is the slope of this line? Yeah?
150 over 3, which will be the time.
Right. So you find the slope. It'll be 150 over 3. You can know that as rise over run. You can also, if you wanted to, call this point x2, y2, which is 3, 150. And you can call this point x1, y1, which is 0, 0. You can do the slope formula, but any way you get it, you'd end up with 50 is the slope. Now here is a follow-up question. What does that mean? What is that 50? How does it relate to the situation? That number 50, what is the importance of that quantity? Yes?
The object was moving at a constant rate of 50 miles per hour.
Right. The slope actually tells us how fast the object was moving. If you actually paid attention to the units, you'd realize your slope was 150 miles minus 0 miles over 3 hours minus 0 hours. The answer is 50 miles divided by hours. Or for shorthand, that is 50 miles per hour. Turns out that the slope of that line that we were tracking the distance over time ends up telling us how fast the object was moving. We want to figure out how fast something was moving. It's very interesting that a mathematical calculation gave the answer to that question. So now you're starting to see, hopefully, the idea that we're going to use to our advantage here. This suggests a very powerful thought. That somehow slope is in some way equivalent, or in the sense that can be interpreted as speed, or probably not speed, velocity. We'll make the difference between speed and velocity precise soon. Or a more general term that can be describing either rate of change. Now, I made this an illustration because it seems obvious as to what the answer is here, because you can literally watch the unit, and the units are familiar to you. Miles per hour, that's how fast something is moving, right? Yeah, so it's obvious from this example, but the important idea is the following. This is a graph. It is merely an abstraction of a physical phenomenon. I could have labeled these axes anything I wanted to, technically on paper, and the same calculation should be able to have the same kind of mathematical interpretation. So there the idea starts to become more abstract. One thing you can note is nothing was special about the labeling of these axes. You could have labeled it whatever you want. So you could have labeled something, price versus the profit being made. You could have labeled it as, size of tumor versus amount of chemo. Or something equally morbid, but whatever, you get the idea. You could have labeled it whatever, but that line, if that's how this would be, if that's how the abstraction would work, would end up having to have the same kind of interpretation. This 50 here describes how fast your distance was changing in relation to time. You can know, for example, that your distance is changing 50 times faster than the time is changing. Every time time moves by 1 hour, distance will move by 50, right? A 1 unit increase in your time creates a 50 unit increase in your distance. So now we can talk about speed, but notice that it's a relational speed. I can relate how fast one quantity is changing with respect to how fast another quantity is changing. Every time one guy moves by 1 unit, the other guy moves by 50. You know what? This guy is faster than that guy. By how much? 50 times faster. Right? And we can sort of take away that interpretation. Now that thought is a super important thought. That thought is the beginning of the solution to the rate problem. Really considering that thought, what it means, taking it to its logical conclusion, calculus. Right? That's half of calculus right there. What does it mean now? How can I generalize this? How can I take an idea of a slope of a straight line and apply it to random quantities that we might want to measure, how fast they're changing? Right? So now that becomes the challenge. How do you actually get this done? Because not everything is a straight line. What about a function that's doing whatever it wants to do? Right? Here's some function doing what it do. And let's say I'm concerned about, at this point, how fast is the guy on the vertical axis changing in relation to the guy on the horizontal axis? Now, that question becomes immediately more challenging because it's not a straight line. So we felt happy, okay, slope actually tells us speed, this is awesome, okay, apply it to this. Where do you go from there? So that's what we have to figure out, and that's what we're going to spend most of this class figuring out. Where do you actually go from here? We know how to deal with it in a straight line. How do we get it to work for a curve? The answer, surprisingly, is to think more like a flat earther. So a flat earther, hopefully we all know that the earth is round, but to a flat earther, looks flat, earth is flat. That's the idea. The idea is, sure, something is curving and it's moving and it's bending, but if you zoom in far enough, zoom in close enough, magnify the image large enough, it might seem flat. It might seem like a line, even though technically it's a curve. And that's the idea. That's what we're going to use. What we're going to do is we are going to find a line to approximate the curve at this point. So the idea we have is to form a line. That if you zoom in far enough, the line and that curve are super close together. So close, in fact, that they are effectively doing the same thing. Right? Eventually, if you zoom in far enough, any curve, most curves, not all curves will do this, by the way. So now the curve is going to look almost straight. Sure, it's going to be curving, but the difference between that curve and a line suddenly is not going to be that much. Eventually, if you zoom in, it's kind of like they're doing the same thing. So you kind of zoom in on this picture and you're like, okay, I know how to deal with straight lines, find the slope of a line. How about I use a line, fix it to the curve in such a way that if I zoom in far enough, the line and the curve are effectively doing the same thing. Now I mentioned a couple classes ago, coincidentally, I didn't realize I'd use it now, but coincidentally, I mentioned the importance of approximation to mathematics. Sometimes you can't get the exact answer. You don't need the exact answer, you just need an answer that's close enough. This is one instance in which we're using that idea. I would like to measure essentially the slope or rate of change of this curve. I can't do it. I know how to do it with a line. Approximate it with the line. And what we will do here is we will define the slope of the curve to be equal to the slope of the line that does this particular job. Find the line that does the job of if you zooming in far enough, it'll pretty much be doing the same as the curve is doing. So that's the idea. Create a line that approximates the curve. We'll give this line a name. Call it a tangent line. The word tangent means to touch. And so we call it a tangent line. So basically, if I want to figure out how fast a curve is moving at some point, I will create a line at that point that closely approximates the curve upon zooming in. I will call this line a tangent line. And I will define the slope of the curve at that point to be the slope of that line at that point. And we will be fine with this because the idea is it's a super good approximation. Eventually, if you zoom in far enough, the differences between the two are of no practical significance. We will define the slope of the curve to be the slope of the line. Okay, so that's the first kernel of the idea. We learned that, okay, if something can be tracked by a straight line, we can figure out how fast it's moving by measuring the slope. Cool. How do we do that with a curve? Okay, here's the idea. We're going to draw a line to that point on the curve, and if we get it right, what's going to happen is that line will approximate the curve to such a great approximation that no one's going to care that there's a difference. In fact, we can think of them as one and the same. Okay, cool. How do we get such a line? So far, the only thing I know about this line is a point that it passes through. Now, if all you know is a point, can you define a line? Can you know what that line is? No, right? If you have a point, what else do you need to find a line? You need a slope. The slope is what we're looking for. We don't know the slope. So now the question is, if we don't know the slope, what's the only other way we know to find a line? What's the only way to find a line if we don't have a slope? You need 2 points. You need a minimum of 2 points to find a line. If you do not have the data that tells you your slope, the best you can do is to have 2 points. The problem is we only have 1 point. So now we have to go from a situation of, okay, we need to somehow be able to get a second point in here that will make sense. And what we often do, right? I mean, at this point, the problem wasn't solved yet, and every guess I'm making here can take years between these two guesses because no one knew about this. You know, they were just like throwing darts at the dartboard. So like, the idea came down the pipe hole that let's just pick another random point. Let's just make a random point and then see where we can go from there. So here's our function. This is the point we care about. We want to know how fast the function is moving at that point. This is the line we know we want to find that we're hoping existing. That's a tangent line, but at the moment we don't have enough data to find it. We know that we don't know the slope. The slope is in fact the point of this whole exercise. We need another point, so that's what we're going to do. Let's throw in another point. So we throw in this random point. And we start with what we know. Well, we know how to find the equation of a line that passes through 2 points. So there's some other line here that I can conceive of happening that passes through both the points. One of those points is our points of interest. This line, the line that touches a curve in 2 points of interest, that's given a different name. This is called a secant line. The line that passes through the single point that we care about, that's called the tangent line. That's the line that touches it in 1 point, the point that we care about. Okay, where do we go from here? We have 2 lines. They're obviously not the same line. I care about the line in red, not the line in green. What can we do here? Well, let's just start labeling things. Maybe the numbers will tell us something. Numbers are often very helpful. So let's keep this a little vague because I don't actually know what this point is. Let's call that point X. This point is a random point measured some distance away. That point is going to be x plus some value, h. So I take 2 points and I know the distance between them is h. Okay, so how do we find the slope of the green line? At this point, it's the only thing we would know how to do. Well, the corresponding y value for that is f of x. Corresponding y value for that is f of x plus h. And so the pink line is what we want to get to. We don't know how to get to it yet, but I do know how to find n for the secant line. And that will simply be, well, this is, I call this y2, call that y1, call this x1, call that x2. I use my slope formula, y2 minus y1 over x2 minus x1. You would end up with f of x plus h minus f of x over x plus h minus x, well, that's just h. We end up with the difference quotient. Now we're starting to see a method to the madness, why our algebra and pre-calc professors were obsessed with this quantity. Always having us compute it. For what reason? Why? Why do we need to know this particular thing? It gives us the slope of a secant line, which is one step away from figuring out the rate problem. So now we figure out the slope of the secant line, but again, it's not the slope we want to find. We want to find a different slope. We want to find the slope of the red line. So now here's the idea. What if I fix the point I care about, right? It's not moving, that's the point I care about. Let's keep our focus on that. But that random point we put in, allow it to move, right? Think of this as a point that's a variable. I can move it. So now what we're going to do is take that point. I want a line over here, but I only have 1 point. I need 2 points to draw a line. So the idea is take this point and move it to be right beside this point. Now, if I can move those 2 points close enough together, close enough that it makes no practical difference, the approximation would be pretty much the answer I'm looking for, then I'd be able to, this green line will seem to fall right on top of the red line, which I care about. Then I would have the 2 points, right? Then I'd have the 2 points I need to get this line to pass through by simply making this point super close to that point such that, you know, we might as well assume they were in the same position. So now the question is, how are we going to do that, like legally speaking? I mean, that's wishful thinking. But now the question is there machinery, mathematical machinery or theory that would allow us to move something close and close and close and close and close enough to something so that they're practically in the position we want them, even though technically they're not. Right? We'll never actually get to this point. We can't have the 2 points on top of each other because we can't find a line that way. But I want this to be coming super, super close to this point, but at the same time never actually getting there. Do we have a mechanism to do that? Yeah.
Limits.
That's exactly what a limit is about. So someone came here and like, what are we going to do? Well, we need a way to get this point closer to that one. I don't know a way to get to the point closer to that one. Okay, went over here, they invented limits. Okay, here's how limits work, let's figure this out. All right, this is what it means to get close to something. Now let's come back. Now we have a machinery, the mechanism, to actually do that thing. Essentially what we can do to make one point get close to the other one, consider the distance between these 2 points and let that distance go to 0. Let the distance between the 2 points approach 0. It's never going to get to 0 because then we don't have 1 point. But it can get close enough to 0 that there's no practical difference between them being the same point. And so that idea brings us to the slope of the tangent line, which is what we wanted all along. Start with that, but use a limit to close the distance. And we end up with that expression giving us the slope of the tangent line. Now in class I've repeated this several times. You really want to learn the basics, learn the fundamental, because a lot of times a complicated problem is really just a lot of simpler problems in one, right? And on a macro scale, all of mathematics is kind of like this, right? We have a complicated problem that we need to figure out. We just use a much simpler problem and adapt it to this, right? We know how to find the point between the equation of line between 2 points. How do we figure out? Well, we take that and we just tweak it a little bit to be able to find the equation of a line through 1 point without knowing the slope. Now this is a very important limit. In fact, it is the answer to the rate problem. How do you figure out how fast something is moving in relation to another? Compute that limit. It will tell you. So this is an important quantity, muy importante. I'm not Spanish, but I feel like it deserves to be said in multiple languages. And so, because it's so important, we give it a name. We call it, all together now, do we know? The derivative. Now I don't know why they chose the name derivative. It seems like a very strange naming convention. Like I said, math people are usually very non-creative when it comes to naming things. Here's a theorem that helps us find the intermediate y value given two outer y values. What do we call it? Intermediate value theorem. Here's a theorem that says the average value of the slope is equal to the mean value of the slope. What do we call it? Mean value theorem. This theorem is fundamental to the study of calculus. What do we call it? Fundamental theorem of calculus. But for some reason, here they're like, this allows us to find the slope of a line through 1 point without knowing a second point. What do we call it? The derivative. Yeah! They put on their shades and they walk out the door like, kind of saucy, I like it. We call it the derivative. And it is no simple limit. This is the solution to the rate problem. This limit allows us to say how fast a quantity that we plot on the vertical axis is moving in relation to a quantity that we plot on the horizontal axis. Let's talk about notation, and then I'll actually write it in a definition. Just write it out nicely. Notations for the derivative. There are many actually, but some important notations that you'd see in a Calc 1 class would be what we call the prime notation. This was the notation that Isaac Newton himself developed. Newton's prime notation. So this means you write F, you put a little notch here. That notch is called a prime. It's like an apostrophe, except you take like an Arial font kind of thing and make it bold. So it's not a 1, it's like a little apostrophe. Which I might just write it with a little notch like that. Everyone will understand what you're talking about. So, and this is referred to as F prime of X, right? Because that thing is called a prime. We also have Leibniz's notation. So calculus was invented independently, but calculus kind of in the form that we know it today was developed independently by these two gentlemen in two different parts, where there's been a feud ever since if one stole research from the other person. Newton kind of came up with his theory first, but whatever. Leibniz also developed this idea of the derivative. He used a slightly different notation though. He called it dy dx, where if we set y equals f of x. So this is the change in y over change in x. D kind of stands for delta. Delta is usually the symbol for change. So in the same way that we thought of miles per hour, that whole division relationship going on, so that's how we came up with this notation. How fast is y changing with respect to x, or in relation to respect to x? By the way, this is So this is referred to as dy dx. That's how you call it. Dy dx. Okay? And that refers to a derivative notation. So now, one thing about this notation though is it's surprisingly very versatile. It is a notation that means the derivative, but you can actually treat it like a fraction in many cases. So sometimes you can split that y off and think of d dx as a fraction multiplied by y. Sometimes you can actually multiply both sides by a dx, and you can actually in many cases treat this as a fraction, and it fits very nicely in the larger mathematical theory. It's seen in a lot of cases as a valid way of solving a problem by just splitting up a derivative notation. Right? So this is called dy dx, and you can think of it as the derivative with respect to x of the function y is another way you can think about it. And with that, we can talk about the general definition here of the derivative. Definition. This is called that y equals f of x be a function the derivative of f of x with respect to x, that stands for with respect to, or in relation to. So in the first example, this would be like our distance, that would be like our time, and we're measuring how fast this is changing with relation to that. So the derivative of f of x with respect to x, if it exists. Now here's a clause we have to throw in. Of course, the derivative is a limit, as you saw earlier. Limits don't always exist. We actually saw that limits won't always exist. And so it turns out that the derivative actually won't always exist for every function at every point. We'll talk about specific instances where it doesn't. But you should be aware, it's possible to not be able to do the kind of thing we just did. Right? A function has to be nice in a particular way for us to actually accomplish that. But if it exists, we call the derivative of f of x with respect to x by this equation. So that's the derivative. Very important equation, half of calculus. This equation is responsible for half of calculus. Take fundamental theorem of calculus super literally. You could argue it's responsible for all of calculus, but whatever. So the limit as the denominator approaches 0 of the difference quotient, we call this the derivative. It's a very important quantity. It answers the rate problem. It tells us how the y value is changing how fast the y value is changing with respect to the x value. That notion is called the rate of change. And that's the formula. So in quizzes, probably on test, maybe even the first one, I will ask you to regurgitate this formula. It's important that you can write this formula down in its entirety. If I ask you, define the derivative if it exists, I don't expect you to just write the difference quotient or even just the limit of the difference quotient. I expect you to state it as an equation where there is a left side and a right side, and over here you would either have the prime notation or possibly you can write dy dx. But the definition of the derivative to you is an equation with two sides to it. It's very important that you memorize rules in their entirety and stop memorizing them in pieces. It will cause you a lot of trouble that is just easily avoided. So if it's not clear at this point, let's make sure that we know about the interpretations of the derivative, so you can kind of know when a problem calls for you finding this. So one, the geometric interpretations are, this is the slope of the tangent line at x. Which we define to be exactly the same as the slope of the function itself. because the limits make them the same for all practical purposes, right? In other words, you can kind of think at this point as slope as more as a general synonym, derivative as a general synonym for slope, right? So virtually anywhere where you see the word slope, you could replace it with the word derivative and the meaning would remain the same, and vice versa. Okay? So the slope of a straight line, you can even think of it as a special case of a derivative. Okay? Derivative ends up being a larger theory that can cover things, more things than just a straight line. Another way to interpret this in more of a physical sense, it's how fast f of x is changing with respect to y. With respect to x, or the rate of change. At this point, I'm tired of writing out the phrase rate of change. Let's actually abbreviate that ROC of f of x. All of these phrases, they kind of mean the same thing. So if I want to figure out how fast one thing is changed to another, put that thing on the vertical axis, put the other thing on the horizontal axis, find the derivative, that's the rate of change of the vertical guy corresponding to the horizontal guy. This is called the derivative, and it is the solution to the rate problem. Okay, so let's actually do an example at this point, which is pretty much going to be one of the first examples in any calculus textbook. I don't necessarily like following a book, but it's a nice example. You can't argue with this being the first example. Because on one hand, it's not too difficult for you to lose sight of the point, but on the other hand, it's not stupidly trivial, where it's like, what's the point of me showing us that? Let's find the derivative of the function x squared. That is the first goal. So, f prime of x we know is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Write that down every time you're about to find a derivative. This definition needs to be burned into your brain, especially if it's the first time you see it. Every problem you do where you're finding a derivative, write the formula down so that you eventually remember it in your sleep. Okay. So that's the derivative. So now let's start applying this. What is f of x plus h for this function?
X plus h squared.
X plus h all squared. Common mistake is to just write x squared plus h, not the same thing. X squared plus h, that is f of x plus h. It's not f of x plus h. Remember how functions work? Whatever is in the parentheses replaces all the x's with it in the formula. Okay. So it's the entire, you take x plus h, replace x with it, so you get x plus h all squared minus f of x, which is x squared, over h. Now we need to compute this limit in order to say what the derivative is. How do we do that? Yeah?
We have to cancel the h in the denominator.
Right, h is a problem because you want to be able to plug in h equals 0, but h is in the denominator, so we need to somehow get rid of that h. And so how are we going to get that cancelled?
Expand x plus h
And so that's x squared plus h squared, right?
plus 2xh.
Right. Another common mistake there. Three terms, it's expanding a binomial. A plus b all squared is a squared plus 2b plus b squared. And we end up with that. You'll see right away that the x's cancel. I know, we can cancel these h's, right?
No.
Cannot cancel across sums. Do that, Jhevon will kill you. Okay, what do we do? H is a common factor, you can factor it out. We'll be left with 2x plus h. Now what?
Cancel h.
Now we can cancel the h because there's a multiplication separating the terms. So I end up with the limit as h approaches 0 of 2x plus h. And what's that limit?
Yes.
Now that's just 2x because I'm allowed to plug in h equals 0. I want you to notice I keep, oh my god, I keep writing the limit until I actually take the limit. Once I plug in h equals 0, I can say I take the limit. Now, take the limit. Until that point, keep writing down the limit. Okay? Now, after we take the limit, that becomes the answer. And in other words, that's the answer. That is the derivative of x squared, i.e., if your f of x equals x squared, then your f prime will equal 2x. F prime is the slope of the function x squared. Another way to write this down, shorthand, which I'm often going to use, is to kind of use Leibniz's notation to say this concisely. We can also say the following. I can say d dx of x squared. You know, it's kind of like dy dx. Derivative of x squared with respect to x is 2x. And that's like me saying this entire statement in one short equation. The derivative with respect to x of the function x squared is 2x. That's what that means. Now, what does that mean? Now we'll see many other interpretations here and applications, but for now let's focus on the geometric interpretation. What does it mean that the derivative of x squared is 2x? This means 2x is a formula that gives the slope of the tangent line to y equals x squared at the point x. Let's follow up with an example here. Using the same function, so we can sort of start relating things. Example, I could actually define the equation of the tangent line. To y equals x squared at x equals 2, right? This could be a problem. In fact, there will be problems that ask you exactly that. Okay, so I could ask you that question. And what you would do is, for one, you would find y prime. So you say y prime equal to 2x, calculations above. And so now you would say, secondly, at x equals 2, which is the point that you care about, your y prime would be equal to 4. Now that number 4 is interpreted as what? What do I think of that? That's the slope. Slope of what? Of what? The tangent line. Exactly the same thing what we want to find. Okay, so now I know the slope of the tangent line. How do I find the equation of the tangent line? If I have the slope, what else do I need? Yeah? You need the what?
The equation of the tangent line.
Okay, well how would you know the y-intercept?
You take the point and then you just plug stuff in at x equals 0.
Yeah, plug what in?
The
Yeah, the next thing is to find a point. Perhaps not specifically the y-intercept, because we'd have to do a little jumping through hoops to get there. But I can specifically find the point of interest, the point where x equals 2. So the point is going to be 2, 4, because you remember your y is x squared. So when x is 2, your y is going to be 4, so that's the point. That's like your x1, y1. And so now you can go to the tangent line. Y minus y1 equals mx minus x1. Y minus 4 equals 4 x minus 2. And that's the equation of your tangent line. Or if you prefer mx plus b, which in general I probably wouldn't care, but here it would be 4x minus 4. So here's what that means geometrically. Basically, I have the function y equals x squared. I want to know what's going on at the point 2 in terms of the rate of change. I know how we would do that here is to find a tangent line. And so now I might ask, what is the equation of that line? Well, it will be the line with slope positive 4 that passes through negative 4 on the y-intercept. This will be the line that's going to be the line. This is the line y equals 4x minus 4. That is the tangent line to x squared at the point x equals 2. The derivative helps us find that line. We're going to stop there. Are there any questions? So later on we'll develop some nicer formulas, easier ways to talk about derivatives, but until then, let that idea sink in.